learners. I'm Mrs Mugisha. Today I'm going to give you a kind of run out of, or a quick check out of the sections you should be doing in this module. The textbook you use is 3rd edition, Calculus, Early Transcendental Functions by Smith and Minton. And I'm mentioning this book specifically with the sections which you should be covering, because most of you keep on handling or doing the sections which you are not supposed to be doing. So if we go to the table of contents of this textbook, I want to do this before I start anything for today. You're going to do chapter 0, which is preliminaries. Now these ones, you're supposed to know these things from the high school for you to remember the functions, the types of functions, inverse functions, trig functions, exponential functions, and the rules which goes with those kind of functions. So you do the whole chapter 0 to remember. If you know everything, then just run through it and then go to chapter 1. So chapter 0 is compulsory for this module. Now chapter 1, you do all the sections in chapter 1, that is 1, 1, 1, 2, 1, 3, 1, 4, 1, 5. Those you are supposed to know them, and they will be for the exam purposes. But when you go to section 1,6 from chapter 1, and this one, in the study guide, they said you should know it, but not for the exam, but just to understand, because they wanted to know, just to have an idea of the formal definition of a limit. So this is section 1,6, but it's not for the exam purposes. And then 1,7, just read through it if you want, just to expand your knowledge. Then chapter 2, you do the whole chapter 2 in this textbook for the Maths 112P. You don't do chapter 3, jump chapter 3, but most of you are wasting time doing it. But those who are doing Maths 113Q, maybe you can do this one. But now we are just concentrating on materials for 112P. So chapter 0, chapter 1, sections 1, 1 to 1,5, 1,6, just read through. The whole chapter 2, and jump chapter 3. Then you go chapter 4. Chapter 4, I would like you to do 4,1, 4,4, 4,5, 4,6, 4,8. But also, I would like you to read through 4,2, 4,3 for you to have the understanding of the areas under the curve when you use the triangle method and so on. So just read through 4,2 and 4,3 for understanding. 4,7, you are stretching your knowledge, but actually the material here is 4,1, 4,4, 4,5, 4,6, and 4,8. Then in chapter 5, you do 5,1, areas between the curves. And in chapter 6, you do review of formulas and techniques. That is only section 6,1 only for this chapter. And then when you go to chapter 7 on the first order differential equations, you're going to do section 7,1, 7,2. And that's all. Then we jump again and go to chapter 12. And in chapter 12 here, we are looking for partial derivatives. So that is 12,3. And also go through to stretch on 12,3, go and do 12,5, the chain rule of partial derivatives. So that's the material you are supposed to know, or the sections and chapters with the corresponding sections for Maths 112P. Now, we go today. I would like you to go and welcome to this session, the first day. Now, this day, you're supposed to know the functions. And now the functions, these ones, you know that you're supposed to know them from high school. What the types of functions, remember one-to-one, many-to-one, and so on, continuous functions, and so on, all the properties and rules which go with functions, because you need function to be able to handle the next topics. Now this one, I'll ask you to read. We are not going to do much about this one. Then we are going to do limits and see the types of limits we are faced with in this module. And then at the end, we are going to do continuity. So I would like to go through all these 3 sections, and then at the end of everything, you can ask questions. I think you'll be warned when you're going to give or when you're going to have questions session. But actually, I would prefer sections coming at the end of the session. Let's continue. Okay, functions. I didn't do anything there. I would like you to read about functions, please, and then just see the types of functions. And then here, we are going to do limit. And I want you to understand what the limit means. The limit means is the y value or the height of a function when you put in the x value in a function. Now, this kind of function is kind of rational function. Now, it will be discontinuous if you don't redefine it. Because if x is equal, it will be discontinuous when x is equal to 2. That means that you cannot find the domain or the y value or the range when you put the x is equal to 2, because you'll be dividing by 0. Now this, but then if we define or we rewrite this function or factorize the top, and then we cancel with the one at the bottom, then it will be a function and so on. But our main thing is to know that this has a limit or not. Now this is the expression we are faced with. And now when we are talking of a limit, you say that find the y value or the limit value as x approaches to 2, either from the left or from the right. Or when x not really equal to. You use the y value, you find the y value when x is equal to 2. But we don't say equal to, we say approaching, because the limit value. Now here, when you see these values, these are values less than 2. So 1,9, 1,99, but 1,999, you are approaching 2 almost from the left. Why? Because you are approaching 2, but not exactly equal to 2, and it's less than 2. So these values of x, they are called y value, x values approaching 2 from the left. And then these are the y values, you get the corresponding y values, you put in the function, and then you get this y. When you put in x is equal to 1,9, you get y is equal to 3,9, and so on, and so on. Then you get this one. Now you say that as x approaches to 2 from the left, the y value or the limit value is approaching to 4. And that means that here it's read that as x, the limit of f of x, this particular function, as x approaches 2 from the left, it's not minus 2. You're approaching 2 from the left-hand side of 2. And then when you plug it, that value is equal to 4. And it's read from here. Is approaching to 4 or is equal to 4. And when I'm taking this is known as the left-hand limit. When I'm taking the right-hand limit, also you see that I'm approaching 2 from the right. I'm approaching 2 from here, but it's greater than 2. That's why I'm saying 2,1. So I'm approaching 2 from this side. When I'm approaching 2 from the left is this side. And all the values of x are less than 2. When I'm approaching 2 from the right, I'm on this side of the 2. And that's why I said I'm using 2,1, 2,01, 2,001, 2,00. I'm approaching 2 from the right, but not exactly 2. So when I'm plugging the values of these values in the function, I get 4y is equal to, or the limit value, which is the y value, is equal to 4,1, 4,01, 4,001, and so on. You can see that actually the value is approaching to 4. So here we say that the limit as x approaches to 2 from the right, oh, here it's written, from the right, where am I? Here, I'm approaching 2 from the right of this function f of x is equal to 4. Now, the limit of this function f of x, as x approaches to 2 from the left or from the right, the values are the same, is equal to 4. Then we can say that this limit exists. So mathematically, we say that the limit as x approaches to 2, you see I'm removing left-hand side and I'm removing the right-hand side. So I'm just saying x approaches to 2 of this function f of x, the y value is 4. Then this is the limit value. That means that the limit exists. Why? Because the left-hand limit, which is 4 here, I'm approaching 2 from the left, and the right-hand limit, which is 4. Why? Because I'm approaching 2 from the right. That's why it's known as the right-hand limit and the left-hand limit. Both values are the same. Then the limit exists as x approaches to 2. So I combine the left and the right together, and I just write 2. The next, and the graph, you can see graphically here, you see that actually the y value is 4 as I'm approaching 2 from the left, or I'm approaching 2 from the right. The y value or the height of this function is 4. And here we get the linear function, because if I leave the function like this, then it will be undefined. But for this function to be defined, I'm going to factorize the top, which is x minus 2 into x plus 4 over x minus 2. The x minus 2 cancels out. I remain with x plus 2. And that's the linear function y is equal to x plus 2 with that positive slope. And it goes on. Now, consider the second expression, a function. G of x is equal to x squared minus 5 over x minus 2. The same thing, we do the same thing. If I take the left-hand limit of this expression, I can't factorize this one, I can't cancel this one. But if I put in 2 here, I'm going to get 0, which I can't do. Now, what I'm going to do, I'm going to approach 2 from the left, from the same thing as the former example. As x approaches 2 from the left, g of x is equal to 10. And it came from there. You see it's reducing. As I'm coming closer to 2 from the left, the y value is decreasing, okay? Increasing, I beg your pardon. It's increasing, and so on. Now, as I'm approaching 2 from the right, 2, 2, the y value is kind of decreasing from minus 5,9 to minus 9,995. And so you can see that it's decreasing as I'm approaching 2 from the right. Now, you see that when I'm approaching 2 from the right of this function g of x, I'm getting minus 9,996. And as I'm approaching 2 from the left of this function g of x, I'm getting 10,400 or something. No, actually, yes, 10,000. Now, you see that the two values are not the same. So since the left-hand limit is not the same as the right-hand limit, then the limit of this expression, which is written like this, does not exist. Why? Because the left-hand limit is not the same as the right-hand limit. And even when you continue, you can see from the sketch that actually, as I'm approaching 2 from the left, the y value expands or explodes to plus infinity, almost. It goes upward. But when I'm approaching 2 from the right, you can see that the expression is going down to minus infinity. So the two values cannot converge. Then now I would say the limit as x approaches to 2, I'm rounding off, I'm combining, approaching from the left and from the right, then say as the limit of g of x as x approaches to 2, there's no minus, there's no positive, does not exist. Why? Because the left-hand limit is not the same as the right-hand limit. Now, we go to the definition of the limit. Now, the limit exists if and only if corresponding one-sided limits are equal. This is that the left-hand limit is equal to the right-hand limit. And which in general, we write it that in general, we say that the limit as x approaches to a of this function f of x is equal to some values of L, where L is a real number, if and only if the left-hand limit, the limit as x approaches to a from the left of this function f of x is equal or the same as the limit as x approaches to a from the right of the same function f of x, which is equal to L. Then we say the limit as x approaches to a exists. And now let's consider some examples. Now, this one are the types of cancellation. We are going to see the types of the limit. Now, the types of the limit, the kind of limits we have faced with here in this example, on this section, they are kind of simple ones, but given or presented in a different ways. Now, when I'm talking of cancellation limits in these examples, for example, we're going to do this example for ours. I will say that cancellation type of limit. The first one, they say that find the limit as x approaches to 2. Thank you. As x approaches to 2 of x squared minus 4 over x cubed minus 8. Before you do anything, the first thing you do, you get your value 2, plug it in. When you put, wherever there's x, you put your value of 2. Now, when you see your value here, I'm approaching 2 from the left. I'm approaching 2, not from the left or from the right. It's just I'm approaching 2, or is equal to 2. So I'm picking this value, my 2. My x value is 2. I go and plug it in or substitute it wherever there's x in my expression. And there, what am I going to do? Let me write it. I'm going to plug wherever there's 2, wherever there's x, I'm putting 2. So it's going to be 2 squared minus 4 over 2 cubed minus 8. But then here you see that I have 4 minus 4 is equal to 8 minus 8. So it's going to be 0 over 0. So I cannot conclude. I don't know if you can read that one properly. So I can't conclude. Now in this case, since I cannot conclude, I have 0 over 0 or infinity over infinity. Maybe sometimes I can have infinity over infinity. So I cannot conclude that is equal to 1 or is equal to 0. No. So what am I going to do? I'm going to say that this is a kind of indeterminate form. I have to work on the expression. This kind of, that's why we are calling it cancellation. Cancellation because I'm going to factorize this expression and have x approaches to 2. This is the difference of 2 squares. Then it's going to be x minus 2 into x plus 2. This is the difference of 2 cubes. So I'm going to have x, remember, this is written as x cubed minus 2 cubed. Now here, the difference of 2 cubes, you get out the first term, which is x, get out this with the corresponding sign, get out 2, the second term, which is 2, that gives me the first factor. The second factor, which is quadratic, I square the first term, which is x squared. The product of first term and second term, which is x multiplied by minus 2, which is minus 2x, with opposite sign, then it becomes plus 2x. Square the second term, which is minus 2 squared, which is 4. That gives me the second factor in the difference of 2 cubes. Now I see this one here, there's x squared, x minus 2, and I have x minus 2, and it's a product on top and product also on the top. This cancels with this one. Then I'm going to remain with limit, the expression as limit, as x approaches to 2 of x plus 2 on top. At the bottom is going to be x squared plus 2x plus 4. That's my new expression now. So that's why they say cancellation, because I'm going to cancel one factor from the top and one factor from the bottom. Now, I have a new expression. After doing this, I'm going to plug my x is equal to 2 wherever there's x in my expression. So here I have 2 there, so I'm going to have 2 plus 2, if it's possible, over 2 squared plus 2 times 2 plus 4, which is not affected there. So my conclusion is going to be 2 plus 2 is 4, over 2 squared, which is 4, plus 4 plus 4. Then my outcome is 4 over 4 plus 4 plus 4, which is 12. Then my answer is going to come. Then I can simplify this one is 4 over 12, which is, I can have 1 over 3 by 4, if you cancel by 4. Now this, I get a real number. This is my y value or the limit value. Then I stop. Now you see why I have to do all this, because I'm going to cancel. It's called cancellation type of limit, because when I plugged in my value of x at the beginning, when x is equal to, I got 0 over 0. Actually this one, I'm just adding on here. But I get 0 over 0. I cannot conclude. Then I have to tell myself, what am I going to do to this expression for me to get out of trouble like this? And then I start factorizing. Then I factorize. After factorization, I see which factors to cancel. Then write the expression in the new form. And then from there, plug in my x value, which is 2 again. I get, if I end up with 0 over 0 again, or infinity over infinity, then I'm going to rework on to rewrite the expression again, or see what to do in the function expression again. But in this case, I see that I get a real number. Then I conclude my limit value is 1 over 3 or 4 over 12. And then I stop. The second example is going to be limit as x approaches to a. Remember, always you don't have to have a real number. We have a variable here as x squared minus ax plus x minus a all over x squared minus a squared. Now here I have x, all variables. I have a constant a and I have a variable x. Now they said find the limit of this. But of course, when I see my expression here, I'm not going to get a real number really, because the expression I get, it will be in terms of a, because I don't have the real value. Okay? Now what I'm going to do here, factorize by grouping. Factorize the top, factorize by grouping here. Factor by grouping on the top. On the top. Okay? So what am I meaning when I say factorize? Because I have 4 terms, and the only way I'm going to find the factors of this I will by grouping. So I'm going to say limit as x approaches to a. I'm going to group to make my life easy. I'm going to group. I'm going to group these 2 and these 2. Then I have to get my factors. So I'm going to have x squared minus ax plus, with the plus here, x minus a. That's the first one. Then all over, the difference of 2 squares here, so it's going to be x minus a into x plus a. Now here I have not finished, but grouping here again, I continue writing my word limit until I substitute my value of a, my value of x. So as x approaches to a, factorize this one again. The common factor here is x. So get x out again. Here I remain with x here and a there. I have not finished. Plus x minus a. This factor here hasn't gone out. And then here x minus a into x plus a. I continue, haven't finished. Here I see I have this term here and that term there. Now here I have x minus a and I have x minus a. So I have x minus a in common in 2 terms. Then I'm going to say limit as x approaches to a. Here I'm going to get x minus a out as the common factor here. And then here if I get x minus a, I'm going to remain with x here. And then here when I get x minus a, I'm going to remain with 1 all over the difference of 2 squares into x plus a. Now I see cancellation. Cancellation comes in because I have x minus a there, I have x minus a there. This goes. And I did this one because when I plug my, why I have to do all this? Because when I plug in my x here, my a, I will get, let me use this color. If I plug my a from the beginning, I'm going to have a squared minus a squared plus a minus a all over a squared minus a squared. So if I go through, I see I get 0 over 0. I can't conclude. That's why I have to go and find the factors of this expression so that I cancel some of the factors and then I remain with another and then continue. Limit as x approaches. I haven't stopped writing a again because I have my expression here, x plus 1 over x plus a. Now, I'm going to plug in my value of x as x approaches to a. Whenever there's x here in my expression, I'm going to put my value of a. So here I'm going to stop. I don't write the limit anymore. So I'm going to say a plus 1. Wherever there's x, I put a. That's a constant that is not affected. Over where there's x, I put a. And there's a there from the constant originally. So I'm going to have a plus 1 over 2a, a plus a. So my limit value is in terms of a. Why? Because I don't have a real value of a. If I had a real value of a, then it would be a real number. So this is my y value as x approaches to a. And my y value is in terms of a constant a. So these are the 2 examples of cancellation types of limits. The third one, which I also want you to handle, is the limit, which is 3 here. I will say B. The type of the limit you're going to have, the limit of the type as x approaches to plus infinity, plus or minus infinity. Now here, infinity is not a real number. It's just infinity. We don't have exact value. But they're still asking us to find the limit as x approaches to infinity. So example is find the limit as x approaches to plus infinity of 6x squared minus 1 all over 2x squared plus 7x. Now, this is an infinity type of limits. Now, before you do anything, as I said, plug in your x value to see what kind of expression or what are you going to end up with. So whenever there's x, put in your infinity. So this one will be infinity over, put in your infinity here, it will also be infinity. So I have infinity over infinity. I can't conclude that is equal to 1. No. So what am I going to do? I'm going to see on what to do with this kind of expression. Now, what I want to explain that if you're asked to find the limit of a rational function like this, and you go to the denominator, look for the highest power of your variable x. In this case, my highest power is 2 in the denominator, not in the numerator, in the denominator. I'm doing this when I'm taking my limit, when I'm finding the limit as x approaches to infinity or minus infinity of a polynomial over a polynomial. I go to the denominator of this expression, rational expression, pick the highest power of the denominator of the variable. In this case is x to the power 2. It's also on top, but here because it's at the bottom. And after that, divide through that power of x to the power 2 through each term, limit as x approaches to infinity of 6x squared. Remember, my highest power of the variable is x squared. So divide that x squared through each term separately, all over 2x squared over x squared minus plus 7x over x squared. So when you cancel, you have limit. I haven't finished writing the word limit. As x approaches to infinity, this one here, the x squared cancels with this x squared. I end up with 6. It remained there, x squared, 1 over x squared, all over, oh, thank you. Then 2x squared over x squared, this x squared cancels here. I remain with a constant 2, plus here, plus 7. 7 here of x. X will cancel with this one, x here. I remain with 7 over x. Now, in that case, I start plugging in my infinity now. Remember, this is a constant. I stop writing the word limit. Then I'm going to have a constant there. If I put my limit as x approaches to infinity here, my x approaches to infinity here, it's a real number over a very big number over infinity. You know by definition from high school is 0. Any real number over infinity is 0. And over divided by a constant, which is 2 there, plus any real number divided by a very big number, in this case it's infinity, is going to be 0. Then I'm going to have 6 minus 0, which is 6, over 2 plus 0, which is 2. And if you simplify, your limit value is 3. So this is an example of where you are asked to find a limit of a function where you have a polynomial of a polynomial and your x approaches to infinity or minus infinity. The main thing to remember here, you pick the highest power of the variable in the denominator, not in the numerator, in the denominator, and divide it through each term. That's how you handle this kind of examples. Now, another type of limit I want you to know is the absolute values, the limit values which involve absolute values. And I found that actually these kind of limits are giving students a lot of problems. But it's the same thing. Now, in high school, remember, you got the definition of absolute value. Absolute value of x is equal to the inside x is positive if that inside x is greater or equal to 0. And the inside is negative, that means minus x, if the inside is less than 0. Now this gives you the functions in 2 sections. So you come from this expression, you end up with 2 linear functions here. But in this case, or any 2 types of function, it could be quadratic or linear, depending on what is inside x there. Now here, you have this one from the high school. Now another example which I wanted to kind of highlight here, where most of you are making problems. Here we are dealing with x here, inside alone. That's why it's x, and x is greater or equal to 0. Here it's minus x if x is less than 0. But if you have more than one term inside the absolute value, inside the 2 straight lines, then you're going to say that the inside, which is 3 minus 2x, is equal to, here you have absolute value of 3 minus 2x is equal to 3 minus 2x is positive if 3 minus 2x is greater or equal to 0. The inside, most of where I want to say here, you are going to say, let me explain this one. I want to explain this on this board. You say, if I have 3 minus 2x, I want to say the inside is 3 minus 2x if 3 minus 2x is greater or equal to 0. The inside is positive if the inside is greater or equal to 0. So most of you, where I'm going to highlight here, you would say that this is right. You would say is equal to 3 minus 2x if x is greater or equal to 0. And then you don't say x. Well, actually, the one you want is this one. This is wrong. That's right. But most of you, you just say x because x is always in your mind. But here, actually, we want my x now is the inside, 3 minus 2x. And then you go and say the inside is negative minus, with the bracket, 3 minus 2x if the inside, again, 3 minus 2x is less than 0. And then you have two sections. So when you simplify this one, you're going to say 3 minus 2x if, now you're going to solve this inequality. You solve this inequality. So take x that side. When you get it, actually you're going to have if x is actually less or equal to 3 over 2. Why? Because I'm putting 2x, 3 that side. I keep minus 2x on the left-hand side. Minus this 3 becomes minus 3. And then I'm going to have, let me do it here. It's going to be minus 2x is greater or equal to minus 3. And then here I have x, because I'm dividing through by minus 2. Then the inequality will change from greater or equal to less or equal to minus 3 over minus 2. Then that's why the answer is less or equal to positive 3 over 2. So that's why I have my section is going to be, my function, my absolute value definition is going to be 3 minus 2x if x is less or equal to 3 over 2. And also, I remove the bracket here. I remove the bracket from here. Then it's going to be minus 3 plus 2x if x is greater than 3 over 2. It comes from this expression, solving this inequality here. And then you get this one. Why the inequality changes from the negative, less than to greater than, because I'll be dividing through by negative, like here. And then I end up with this one. So this is my expression of this one. So I wanted to give you this example to remember that really whenever you say you have given an absolute value, you're applying the definition. Here you get it out, the inside is positive, or if the inside is positive or equal to 0. The inside is negative if the inside is less than 0. Then solve those inequalities to get the value, the boundary value. So this is where I wanted to explain the absolute value definition. Now here, you are going to be given, they ask you, find the following limit. Find the limit of x minus 5 over absolute value of 3 minus 2x as x approaches to positive infinity. Now here, I'm going to have x minus 5 over this as x approaches to infinity. I'm going to apply the definition of my absolute value, which we did on top, which we did here. Now this absolute value, I'm going to check. Actually, I wanted to notify here. The value I'm picking here, the value I'm picking here is minus 3 plus 2x. Where does it come from? It comes from the definition I had here. We say that my inside is positive if x is less or equal to 3 over 2. And I consider this part. For all the values less or equal to 3 over 2, I consider this part of the function, which is 3 minus 2x. And for all the values, which are greater than 3 over 2, I consider this part of the function. That's why here I chose minus 3 plus 2x to put here. Why? Because as x approaches to infinity, it belongs to x is greater or equal to, is greater than 3 over 2. So that's why I chose this part of the function. Now I have this expression. It's a polynomial of a polynomial. Pick as x approaches to infinity. Pick the highest power in the denominator, which is x to the power 1. Divide through x to the power 1 through each term, which is x over x minus 5 over x over minus 3 over x plus 2x over 3 over x, sorry. Then I end up with the limit as x approaches to infinity, 1 minus 5 over x all divided by minus 3 over x plus 2. And then there, I plug in my infinity in each term here. This is a constant, is not affected, I write it there. Plug infinity here, it's 5 over infinity is 0, so it's going to be 1 minus 0. Here, still, minus 3 over infinity is minus 0, because it's positive, because here I have infinity. Why it's minus here? Check the sign. It's minus 3 over positive infinity, so it's 0. I know it's 0, but with negative. And then here, plus a constant 2. Then I end up with 1 minus 0, which is 1, over 0 minus 0 plus 2, which is 2. My limit value, or the y value as x approaches to infinity of this expression is 1 over 2, or a half. Now, we extend our definition of limit, of finding the limit, to the left-hand limit and the right-hand limit. I had explained earlier on why do we call it a left-hand limit and why do we call it a right-hand limit. Now, a left-hand limit is the y value you obtain by approaching the x value from the left, as the first example. And the right-hand limit is the y value which you obtain by approaching x value from the right-hand side. Now, we can see one example in this nature. This example is given as h of x is in 3 sections is equal to x if x is less than 0, is equal to x squared if x is 0, x is between 0 and 2, and is equal to 8 minus x if x is greater than 2. So my function h of x is defined in 3 sections. They say that I have this function has got 3 sections. They say that for all the values on the left-hand side of 0, you consider the part x, the function x, y or h of x is equal to x. All the values of x between 0 and 2, 2 included, you consider the part of the function x squared. That means h of x is equal to x squared for all these values here. And all the values on the right-hand side of 2, greater than 2, you consider this part of the h of function x, 8 minus x. So this is known as a function defined in sections. That's why I told you that with absolute value, the functions can give you, we end up with a function in absolute, in sections. So this is an example of function in sections. How do we find the limits? Now here, we say, get the limit as x approaches to 0 from the left of this function. And the function is given up above there. Now, you go. Look for the function. Remember, I'm approaching 0 from the left. Go here and look that actually I'm approaching 0 from the left is like less than 0. So this is the interval I'm dealing with. X is less than 0 in this function. Now, since this is the interval I'm dealing with, this is a part of the function I'm going to choose to put in my f in place of this h of x. Then I put x there, and if I put my value of x which is 0, I end up 0. Then again, find the y value or the limit value of each h of x as x approaches to 0 from the right. From the right, I go back, I look from the right. Is like greater than 0. This is here in this interval here, belongs to this interval because I'm approaching x0 from the right. So I pick this function. So the part of the function of h I'm going to use is x squared. So I go back and replace my h of x here with x squared. Replace x by 0, I get x0 squared, I end up with 0. Now, the left-hand limit as x approaches to 2 from the left of this function h of x, I'm going to say also which function am I going to pick? I'm approaching 2 from the left. From the left is here, or equal to 2 is here. So since the interval x approaches 2 from the left belongs to this interval, then I'm going to use this function. Then I go back and I said, okay, as the limit of this function as x approaches 2 from the left, I'm going to replace that h by x squared. That's the part which corresponds with this value, this interval. Then I'm going to plug in my 2 value, not minus 2, 2. This one means that I'm approaching 2 from the negative side, from the left. It doesn't change the sign of the value. My y value, my x value is 2. So I'm going to go and plug my x is equal to 2. Then it says 2 squared, which I end up with 4. Now, I go again, take the right-hand limit as x approaches to 2 from the right. That's called the right-hand limit. As x approaches to 2 of this function f of x, h of x, I go and see. I'm approaching 2 from the right. It's here. It belongs here. It's greater than 2. Now, this is the corresponding part of the function I'm going to use. Then I go and I said, okay, since I'm approaching 2 from the right, then h is going to be replaced by this part of the function, x minus 8. Go and replace your 2, wherever there's x, put your 2. I'm going to have 8 minus 2, which I have with 6. Now, you notice that the limit as x approaches to 0 from the left, and the limit as x approaches to 0 from the right, the values are the same. So the left-hand limit is 0, the right-hand limit is also 0. So that means that the left-hand at the limit, this means that, therefore, since the limit as x approaches to 0, I'm combining the two, of this h of x is equal to 0, it exists because the left-hand limit of this h is equal to the right-hand limit as x approaches to 0 from the right, which is equal to 0. So the limit exists. But if I go and compare, the left-hand limit of f of x as x approaches to 2, which is 4, the right-hand limit as x approaches 2 from the right, which is 6, these two values are not the same. That's why I'm saying that the limit as x approaches to 2, remember I'm combining the left-hand side and the right-hand side of this, does not exist since the left-hand limit of this function and the right-hand limit are not the same. And it's written like this. Okay? So this means that the left-hand limit of this function f h of x and the right-hand limit of this function as h of x are not the same. The left-hand limit is 4 and the right-hand limit is 6. So the limit as x approaches to 2, as 2 here, it's rounded off, does not exist. Now, limits involving trigonometric functions. Now here, in order to compute derivatives of trigonometric functions, for example, by using the first principle of differentiation, remember if you go back to your high school, we first know how to evaluate the limits of some of these trigonometric functions. And these are given here. Remember, when I'm talking of the derivative, finding the derivative using the first principle, you remember when you're taking the limit as x approaches to 0, as h approaches to 0 of f of x plus h minus f of x as h all over h. That's the first principle of differentiation, the method you used in high school. So when you did those limits, I'm sure you had to know some of the trig functions, the limit of trig functions, which I want you to know here. So some of these definitions are given here. So that you know that the limit as sine x as x approaches to 0 is equal to 0. We get it by just putting 0 in place of x equal to 0. And the limit as x approaches, the limit of cos x as x approaches to 0 is 1. You put 0 in the place of x and get cos 0, which is equal to 1. And you can get them from the sketches or the graphs of sine and cosine, which are very popular in high school. Another limit maybe which you don't know, or another definition which is you should know, and it's in your book of Smith and Minton. They say that the limit as x approaches to 0 of sine x divided by x is the same as the limit as x approaches to 0 of x over sine x. And it's given to you as by definition, as a definition is equal to 1. This one I didn't want to bore you with the proof. There's a proof of this one. I think Minton gives it in the textbook, but I don't think you have to know the proof of this. If you want to know, you can go and look for it, but this is just, you have to know this, that the definition is 1. What I want to explain here is that, remember, x approaches to 0. That means that you have sine 0 over 0, or the limit of x approaches to 0. If you put 0 there, you're going to have 0 there and sine 0. So remember, this must be 0, that must be 0. Or here it should be 0, or this 0. Then by definition, this is equal to 1. I'll come back here, I will expand to this one here. Now here, the limit as x approaches to 0 of cos x minus 1 over x is the same as the limit as x approaches to 0 of 1 minus cos x over x which is equal to 0. So these you should know as a definition. So the limits in the following this one, the limits involving trigonometric function, the first one, you have limit as theta approaches to 0 of sine 5 theta over 3 theta. Now here, remember, what I was saying there, I'll say that, remember here, the limit as x approaches to 0 of sine x over x is equal to 1. Remember, this one approaches to 0 here, equals to 0, here is equal to 0. So it will be like sine 0 over 0, by definition, is equal to 1. Now, this is what we have to keep in mind for us to calculate all our limits of this nature. Now, here, I have 5 theta here, instead of x here. Here I have 3 theta. So I cannot use this definition immediately. I have to rewrite or rework on this expression so that I can be able to apply this definition. How am I going to do it? I have sine 5 theta there. I have 3 theta here. For me to use this definition, I must have 5 theta here. So what am I going to do? I'm going to rationalize this 5 over 5. It's like 1. I'm not changing anything. Then I put 5 here. I combine this 5 with this 3. Then I'm going to have the new expression as limit as theta approaches to 0. This 3 combined with this 3, 5 over 3, times limit, or sine 5 theta over, this is sine theta, combine this 5 with this theta, then I have 5 theta. So I took this 5 with this 3, I combined this 5 on top with this 3, because I need the 5 at the bottom. I need this 5, and to combine with this theta here. Then I'm going to have limit as theta approaches to 0 of 5 over 3 times, let me use another pen, limit as theta approaches to 0 of sine 5 theta over 5 theta. Now this is a constant, it will not be affected. So my answer is going to be 5 over 3 times, by definition, this is equal to 1 because I have sine 5 theta, my theta goes to 0, it will be 5 sine 0, and theta goes to 0 here, it will be 0. So I have this form. It will be in this form. So by definition, this is equal to 1. So it's going to be 5 over 3 times 1. And my answer will be 5 over 3. That's my limit value. This is how you handle this kind of examples or questions you have involving trigonometric functions. Then another one is B, limit as x approaches to 0 of x cot x. Now here, if I put in my 0, it's going to be cot. Remember, cot is cos over sine. And then I'm going to have 1 over 0, which will be undefined. So I'm going to rewrite this expression, so I cannot conclude. If I plug in my value here, I'm going to have 0 times 1 over 0, which will be actually 0 over 0. I cannot conclude, so I can't say 1. Then I'm going to rewrite on my expression here to see if I can get out of this trouble. How am I going to rewrite this one? I'm going to say limit as x approaches to 0, leave x as it is, use the definition of cot. Cot is cos over sine, because tan is sine over cos. Now cot is reciprocal, which will be sine over cos over sine. Now, when I see this one, I want to use my definition, which I know. I want to get out of trouble of this nature. So I'm going to rewrite this expression again. I'm going to say limit as x approaches to 0 of cos alone, cos x, times the limit as x approaches to 0 of x, I remain x on top, over sine x. Remember? So if I plug my cosine, my 0 in terms of x here, I'm going to have 1 times, by definition, this is equal to 1. Then I'm going to say times equal to, so my answer is 1. Okay? It's a product. my answer is equal to 1. So this is how you handle the expressions of the limit of trig functions. But you have to know those definitions which you got from the beginning. The sandwich theorem. When do we use sandwich theorem? And sandwich theorem is like a nightmare to most of the students who are handling Math 112P. I tried to kind of expand on explanation on this sandwich theorem. Now, the sandwich theorem is used to evaluate the limit values of complicated functions or the limit values of the unknown functions. Now, the sandwich theorem is stated as follows. If you have three functions, you have a function f of g, f of f, g, and h. And remember, these all functions are defined or continuous. And for all the x values in an open interval that contains a particular value a, possibly not at a, then we say that the limit as x approaches to a of this function f of x equals, if it's equals to the limit of h and equal to a real value, then the limit of this g is also the L. Now this one, I want to explain it mathematically. I think you can also read in your Minton. So that means that I have three graphs, there's three functions. This is a smaller function. This is a bigger function. G is squeezed in between. That's why they say sandwiched or squeezed in between. That's why they call it sandwich theorem or squeeze theorem or pinched theorem, because G is the unknown function or a complicated function. Then if G is a function which is complicated, I cannot find the limit too easily. But this G is squeezed between H and F. Remember, F is smaller than G, G is smaller than F. That implies that F is smaller than H. So if this is true, if I can find the limit of the smaller function F and find the limit of the bigger function H, and they happen to be equal, then that's the limit of this complicated function in between. This is known as sandwich theorem. I'm trying to elaborate on it using graphical method. And I said that the sandwich theorem, sometimes called the squeeze or pinching theorem, is illustrated by the sketches below. The theorem says that if g of x is squeezed or pinched between the two functions f of x and h of x near a, near that value a, like here, or c, whatever, and if f and h have the same limit value, which we called L, at this value of xa, then G is also forced to have that same limit value L at that particular value of xa. Now, actually, graphically, these are the three functions I'm talking about. The smaller function is h, is at the bottom, The middle function, which is squeezed, which is complicated, is g, is in between. And the upper function, the bigger function h, which is on top, which is in the red color. Now, if we talk of a sandwich, which you make for lunch boxes, whatever. Now, you can see that I'm given the limit, g is inside, is a complicated function, okay, or the unknown function, which is in between, like my feeling here. And then this one on the left is the smaller function, which is my f of x, okay? And this one, the sandwich, this part here, is the bigger function, is a function on my right. And the smaller function is on my left. The bigger function is on my right, which is h of x, the top of, or the above part of the sandwich, or the bread. Then I say that if this is true, if I can find the limit of this smaller function and find the limit of this bigger function, then this complicated function in between, even if I don't know the function here, it will take on the same limit value. So this is how sandwich theorem is kind of operated. Now, the sandwich theorem, how am I using this sandwich theorem? Now, here, the function is given to me. I know the function. If I plug in my value, x squared, as x approaches to 0, I get 0 squared, which is 0. Plug in my 0 here, I get sine infinity. Now, this sine infinity does not mean anything. Sine infinity. Let me do it on the board, here. I have a function. They said define the limit as x approaches to 0 of x squared times sine 1 over x. When I plug in my value of x here, when I plug in my value of x, I'm going to have 0 times sine 1 over 0, which will give me 0 times sine infinity. I cannot conclude anything, no conclusion. Okay? So since there's no conclusion, then I'm going to see how I'm going to find the limit of this complicated expression. That's why I'm telling you that sandwich theorem comes in when we are faced with complicated functions. How do we find the limit of this complicated function? I'm going to find the limit. I'm going to use the sandwich theorem. I'm going to create my f of x, and I'm going to create my f of x. But how I have sign to guide me. I think all the examples you have seen in your book or even the tutorial letters, it's like this one. Now, I have sign expression here. Then since I have sign, it will guide me to use my identity. Remember sign identity. 1, I'm going to keep my x as 1 over x. Is less or equal to 1, less or greater or equal to minus 1. Remember from high school that when my sine function or cosine function is always greater or equal to 1, less or equal to 1, or less or greater or equal to minus 1. So that means that it cannot go beyond minus 1 and it cannot go beyond plus 1. Then I start from there. Now, my aim is to use this expression, this, to rewrite my g. This is my g of x, this complicated function, which I can't find. This is my g of x. Okay? And I want to use this g with this identity to form my h and my f, if it's possible. So I'm going back and use this identity. Why? Because of sign. I remember high school, I know this identity or definition. And then from there, I don't want this expression. I want x squared times sine x. I have this one already. So now here I'm going to multiply sine x. I'm going to multiply sine 1 over x by x squared. So if I do it in the middle, I must do it on the right, on the left, and I also must do it on the right. Then I'm going to say minus 1 times x squared. X squared is positive. The inequality does not change. Either x is negative or negative. As long as I square it, it will be a positive value. That's why the inequality sign will remain as it is. Times x squared positive times sine 1 over x, which I have already on top. Since it's positive, the inequality doesn't change, and I'm multiplying through 1 by x squared. So if I go and rewrite this expression, I'm going to minus. I have minus x squared less or equal to x squared sine 1 over x less or equal to x squared. So I have already formed my g of x. I have my original g of x. Since I already have my g of x, I'm going to stop. So then I'm going to call this one. This is going to be f of x. This is going to be h of x. Then I go back to my theorem, which I have here. I said my g of x here, my f of x is on the left of g, and g is on the left of h. That means h is greater than g is greater than f. That means that f is smaller than h. And it implies that g is squeezed in between. And if this is the case, then I'm going to say, since I've managed to find my h, I'm going to say, therefore, find the limit of h, of your f. The limit of this as x approaches to 0, my original value on top there, of minus x squared, which is my h, which is my f, should equal to 0, is equal to 0 when I plug in. And the limit as x approaches to 0 of h of x, which is equal to the limit as x approaches to 0 of x squared, when I plug in my 0, is equal to 0. Now you see that the limit of f of x, this is my f of x, sorry. If I say limit as x approaches to 0 of f of x is equal to that one. Now, my limit of f of x as x approaches to 0 is 0. My limit of h of x, which is x squared, is equal to 0. So therefore, by sandwich theorem or squeeze theorem, limit as x approaches to 0 of x squared, which is g of x, my g of x actually, let me say g of x, is equal to the limit as x approaches to 0 of x squared sine 1 over x, which should equal to 0 by the sandwich theorem. Because they say that by sandwich theorem, I mean, if you have a function, f of x, which is less than g of x, this is g of x here, this is g of x, f of x is on the right of g of x, and h of x is on the right of g of x. That means g of x is squeezed between the f and the h. And if I can find the limit of f, which is minus x squared here, and I get the value which is L, this is my L here. Okay, we call this L by being our definition. And also this is L. So my L here, which is 0, from the limit of f of x, is the same as my L here, which is the limit of g of h of x. Since those two values are the same, by the sandwich theorem or squeeze theorem, the limit of this g complicated function is also 0. That's how you apply the sandwich theorem. And then I've given you an example. And here, this is an example where you know the g. This is where you know the g. But this example, you don't know the f. Now your f here is g, but it's f here. So you know your smaller function, which is this one here. You know your bigger function, but you don't know the middle function, which is squeezed in between. You don't know. So what do you do? So let me do it here. So this is here why I want to know that this is an example where you have a complicated function, you have a complicated expression, you cannot find the limit easily. So your g is complicated. Here, this is an example where your g is unknown, and in this case we have called your g f. So this is an example of the unknown function f of x. And how do you handle it? The same way. You're going to find the limit. Now you have another example here. You have find the limit. They say find the limit as x approaches to infinity of f of x. You don't know f of x, but, and they say if, they said if 2x squared over x squared plus 1 is less than f of x, and f of x is less than g of h of x, which is x squared plus 5 over x squared. Now, you see your expression when we are talking of the sandwich theorem. We are talking of the bigger function and the smaller function. How do we know this is bigger? This one, because you have 2x squared divided by x squared plus 1. This is x squared plus 1 is bigger than x squared. And here I have 2x squared, the same thing here. Add there something like 5 over x squared. Here, x squared is smaller than x squared plus 1. And this value, 2x squared plus 5, is greater than 2x squared. So that means that this function is smaller than this function. So this is my h of x from my expression there. This was my h of x, sorry. And this is, like we call this should have been g. So this is my g here. And this should have been my f of x from my definition. Okay? So now my g here, or my f here, is squeezed between the smaller function and the bigger function. So what am I going to do? Find the limit of the smaller function. So I'm going to say limit of the smaller function as x approaches to infinity. That is the expression they have asked us to do. Then of 2x squared over x squared plus 1. And we said how to find the limit as x approaches to infinity or minus infinity of a polynomial is you get the highest power in the denominator, divide it right through. I get 2 here. Here I get 1 plus 1 over x squared. So here, if I plug in my infinity, I'm going to have 2 over 1 plus 0. I have 2 over 1. It's 2. That's my limit. For the bigger function, the limit as x approaches to infinity of the bigger function, which is 2x squared plus 5 over x squared. So the same thing, limit as x approaches to infinity. Pick the highest power of the variable in the denominator, divide it through each term separately. Here I'm going to have 2 plus 5 over x squared all over 1. Then here, plug in my value is going to be 2 plus 0 over 1. My answer is 2 here. Now you see that the limit of the smaller function is 2. The limit of the bigger function is also 2. By the sandwich theorem, therefore, by sandwich theorem, or squeeze sandwich theorem, the limit as x approaches to infinity of this function, which is unknown, f of x, is equal to 2 also. This is how we handle the sandwich theorem or find limits of complicated function using sandwich theorem or squeeze theorem. Continuity. A continuous function, a continuous process is one that takes place gradually without interruption or abrupt or quick change. That means that when you're in high school, you remember you are talking of continuous functions. What do they mean? They have smooth curves, no breakage, and so on. Now, the definition here I'm giving short, but when we use the limit of continuity, a function f is continuous at a number a. Remember, the a is the x value. If the limit as x approaches to a of this function f of x is equal to the y value. Here it's written the value when x is equal to a. So that then will say that the function is continuous if this condition is satisfied. The second definition also, they would say that, or another definition, a function is continuous from the right at the number a if the right-hand limit of this function is equal to f of a. The function or the function f is continuous from the left at a particular value of a, x is equal to a, if the left-hand limit of this function f of x is equal to f of a. So that means that we can say the function is continuous when the f of a exists, when the limit exists, and the two values are the same. So mathematically, it's given in this example. So this is a complete definition of continuity when we are dealing with the limits here. Let's say function f is continuous at x is equal to a when the following three conditions are satisfied. The first one, mainly, you always check first is f of a defined? Can you find a y value when x is equal to a? That's the first condition you have to check. The second condition, does the limit exist? That means that can you find the y value when x approaches to a of this particular function? That means that does f of a, the left-hand limit of this function f of x, the same as the right-hand limit of this function f of x? If this is true, then the limit exists. Now, if the limit exists, that means that then this y value, the first value, must equal to the limit value. That this is the third condition. Now, the function to be continuous, the first condition must be satisfied. The second condition must be satisfied. The first condition is that the y value must be defined. The y value must exist when x is equal to a. And the limit must exist. And also the y value must equal to the limit value, that limit value which was found. If anyone or any of the three conditions on top are not satisfied, then you would conclude that the function is not continuous. So that means that the function might fail to be continuous if y value doesn't exist or not defined, the limit does not exist, or the y value exists, the limit exists, but the two values from a1 and 2 here are not the same. That's the third condition. Then the function will fail to be continuous. Those are the three conditions you must keep in mind when you are talking of continuity. And here I wanted to give you the types of discontinuities, okay? In this case, the first one here, you can see the graph is smooth, smooth, smooth. Then I reach here, there's an open here. Now f of a is undefined. It's open here, there's an open I. So the f of a is undefined when x is equal to a. So that means that it's here, the graph is smooth all right through from here to there. When I reach here, I find a hole there. Again, I start. So at x is equal to 2, as x is equal to a here, there's no y value. That means that f of a, y value when x is equal to a is not defined. So this is called as removable type of discontinuity at x is equal to a. When x is equal to a, there's a removable discontinuity. Now another type of discontinuity is in this case here. I have the graph is smooth right through. It's open here. Again, I continue. So it's also discontinuity here. But the y value exists, but it's not the same as, it's not on the graph. It's away from there. So here the limit exists. That means when I'm approaching x is equal. In this case also, if you go back, you say that the limit exists. The limit as x approaches to a from the left, I go to this point. The right-hand limit, that means that as I'm approaching x from the right, I'm approaching a from the right, the y value is there. So the limit exists, but f of a is not defined. That's the first part has failed to be satisfied. Then the function is discontinuous here at x is equal to a. In this example, the limit exists. Now here I see that from here, I'm approaching a from the right, I get this value, y value, that's the limit. As I'm approaching a from the left, I'm getting the same value. The limit exists. That means the left-hand limit and the right-hand limit the same. F of A, the y value when x is equal to A is above here, is not in the same, they are not the same here. So this is a case where the limit exists, f of A exists, but the third condition is not satisfied. The two values are not the same. So this is known as non-removable discontinuity. Okay? So another one, the third one, is where you have the jump here. There's a space here. The function is not joining at all at one point. There's a big gap here. So they call it jump. This is the case where the limit does not exist. The y value exists, is there, but the limit does not exist. That means when you take the y value when you take the limit as x approaches to a from the left, you get this value here. From the right, you get this value here. When you approach a from the right, from the left, you get this value here. Here, this is the case where the limit does not exist, even though the y value exists, but the limit does not exist. This is the example of the jump type of discontinuity, in the case where the limit does not exist, and that's how it's given graphically. So the last one here, this is where also non-removable discontinuity. You can see that when you approach A from the left, the y value goes to plus infinity. Okay? And when you approach A from the right, also you go to plus infinity. Here the limit does not exist. The function value, or y, expands or blows to infinity at x is equal to A. Oh, sorry. Now here, you can say the limit, you don't have a particular value. It's not a real value. It is infinity. The limit is infinity, so you cannot conclude that is equal to 5 or 2 or whatever. So here, the function or the limit, both from the left and from the right, expands to infinity. So I cannot conclude that is equal to a real value. Remember our definition was is equal to L, a real value. L is a real value. So here, it's infinity, it's expanding. So the function, I cannot say that the limit exists. Here, the limit does not exist. So this is another type of discontinuity. To find the function if it's continuous at a particular value of A, you are going to, I want to do this example. Here the question is determine, the most questions you kind of faced with in your exam or assignment or even your textbook. They would say that determine if the function f of x, which is given in sections 1 minus x, if x is less or equal to 2, or also is equal to x squared minus 2x if x is greater than 2. So this is an example where the function f of x is given in 2 sections. So you consider this part of the function for all the values on the left-hand side of 2 and equal to 2. And you consider this part of the function for all the values greater than 2. That means the right-hand side of 2. Now, they are asking you, the question is, determine if this function f of x is continuous or discontinuous at x is equal to 2 or a is equal to 2. And explain why. Explain why it's continuous or explain why is it not continuous. How do you handle these kind of questions? So I have A, this is continuity. I have A, they said determine if the function f of x, which is given as 1 minus x, if x is less or equal to 2, and is equal to x squared minus 2x, if x is greater or equal to 2. My function f of x is in 2 terms. Now they ask me, is f of x continuous? Is f continuous at a is equal to 2? That's the question. Now, actually it should be x actually. At x is equal to 2. This should be 2 there. X at x is equal to 2 here. That should be x. At x is equal to 2. Now, my first step I have to do is I'm going to find the 3 conditions to consider. 3 conditions to check. My first condition is, does f of a exist? 1. F of 2, my a is 2 now. F of 2, does it exist? Y value when x is equal to 2. I'm going to check on this type of function, where here, I can't use this part of the function here. I can't use this one, because here they said x squared minus 2x if x is greater than 2.